Okay, this is the fundamental question, right? We've got two different things we can do, right? We can change the intensity of the light. That just means the brightness of it, right? Okay. Or we can change the color of the light, right? Shorter wavelength. This is a bluer light, right? Okay. Now the important thing you got to understand here is that according to photon theory, making it a bluer light makes the energy per photon bigger. Okay. So this is more energetic, more energy per photon, per particle. Okay. Okay. So let's talk about these, right? If we change the intensity of the light on the electrons ejected from the material, okay, we would have more photons, okay, according to photon theory, right? Okay, we would have more photons, so more intensity equals more photons. Okay, this is I'm talking about what really would happen. Okay, if light acts as a photon in this case, and it does act like a photon. Okay, more intensity just means more photons. Okay, now if you have more photons, you would just have more electrons ejected from the. In fact, if you double the intensity, you would double the photons. It's a very simple, direct proportion. Okay, so you would have more ejected electrons, right? But each photon that strikes the metal would have exactly, since you're only changing the intensity and not the wavelength of it, and this is assuming that the light is all, say, one wavelength, right? They would all have the same stopping potential. They'd all have the same kinetic energy, and therefore they would have the same stopping potential, because this is just how we measure the kinetic energy. Stopping potential is how we measure the kinetic energy. Okay, so we'd have more photons. They would have exactly the same stopping potential. Okay, now if we change a smaller wavelength, okay, if we get a smaller wavelength, then each photon has more energy. Okay, that means that the photons have more energy. Okay, what would that do? Well, here's the thing, right? Photoelectric effect's kind of complicated, right? Okay, so if the photons have more energy, but let's say there's the same number of photons, and that's a little complicated too, right? Okay, because if they have more energy, well, anyway, I don't want to get into that, right? But remember, intensity is watts per square meter, right? So if the photons have more energy per photon, and you make the wavelength shorter, then every photon has more energy. Therefore, to have the same watts per square meter, you'd actually have a few fewer electrons. But let's assume that the number of electrons or number of photons doesn't change. Okay, so the photons are going to have more energy. Well, if they have more energy, right, then you have more kinetic energy, right? Because this equation still holds, right? The photon energy turns into work plus okay, kinetic energy max, right? This is the best case scenario, right? So if we raise this, the work function stays the same, so therefore our kinetic energy rises, therefore the stopping potential is going to rise, because stopping potential is how we measure the kinetic energy, okay? So giving the photons a smaller wavelength gives them more energy, therefore we raise the stopping potential, and that's the most important thing, right? But now let's think about the number of electrons, okay? That photon comes along and it strikes the metal. Remember, sometimes the photon can be just absorbed by the metal, and it doesn't even if it's got enough energy and it's bigger than the work function, okay? It can waste so much energy on heat that it cannot eject an electron, right? It could just hit that metal and just thud, no electron ejected, okay? That's so sad, right? You see the photon go in, it's like, I really want to eject an electron, and it just wastes all its energy on heat, okay? So that's a possibility. But as they have more energy, that's less likely to happen. So you would get possibly more electrons that way, right? And I'm not smart enough to tell you whether the effect of having slightly fewer electrons, because every electron, or sorry, fewer photons, because every photon is got more oomph, right? Whether that would counteract the effect of this being more likely to eject an electron there. Okay, so as far as more electrons, my guess is that there's going to be a few more electrons, right? But the important thing here is the stopping potential. Okay, we're going to have a higher stopping potential. If we change the intensity, we would have the same stopping potential. Now, this is, of course, photon theory. Okay. Well, what did it just do? It's not drawing. It doesn't want to draw. There we go. Can't start drawing there. Okay, that's photon theory. Now, the question on the test is actually contrast photon theory to wave theory, right? So photon theory, the question is the stopping potential or the kinetic energy of the electrons. For this, it depends on the wavelength, right? Because the energy of a photon depends on hc over lambda, right? So making the wavelength shorter makes the photons have more energy, therefore increases the stopping potential, because this is what the photon energy depends on, right? Now, if it's wave theory, then I'm going to erase here, okay? If it's wave theory says that really for the photoelectric effect, what you want is high intensity, right? Because low intensity is, this is low intensity. Remember, wave theory is it's a wave, right? And here's our electric field here. Electric field up, electric field down. Okay, the electric field's what rips the electrons from the atom, right? So low intensity is small electric fields. What you want to do to remove the electrons with great speed is to have a big electric field, right? So you want, you don't want the wavelength to change, right? So this is high intensity is big electric field, right? So high intensity would be fast electrons, so fast photoelectrons, or big kinetic energy, right? And low intensity would be slow photoelectrons, or small kinetic energy. Okay. Right? So with wave theory, and this is why Einstein picked this, right? Okay? Wave theory predicts that all you have to do is change the intensity, and that will change the kinetic energy of the photoelectrons. Okay? But of course, this doesn't happen. Changing the intensity does not change the stopping potential, right? So wave theory has a totally different prediction, right? It depends on the intensity, and it doesn't depend on the color of the light. That doesn't make any sense, right? And of course, when Millikan did this experiment, and it depended only on the color and not the intensity, it was like, what the heck's going on? The only thing that works is Einstein, and we know that's not correct, right? Okay, so just keep that in mind, right? Okay, photon theory says that it depends on the wavelength. On the wavelength, because the energy of the photon is hc over lambda, right? Okay, all right. I think that's it. I think I've said all the words that you can possibly say about this.